Well, hello again. I'm going to continue the plan of attack, which was complex numbers, and then I really hope that that won't take me the whole time and that I'll have some time left to do the last topic, differential equations, at least get a start on that. So, let me just say at the end of last time, or by the end of last time, we had looked at how to add and subtract and multiply and divide complex numbers. Actually, the division was the trickiest part. One more basic sort of operation that I maybe should have mentioned in the same basket is that we can now solve quadratic equations, at least with real coefficients. So if I ask you to find the solutions of x squared plus 3x plus 14 equals 0, and you whip out the quadratic formula, you'll get x equals minus 3 plus or minus the square root b squared minus 4ac all over 2a. Well, 4 14s, 68. No, that's not right. 4 14s are 56. 9 minus 56 is negative 47. Well, in the past we would have said this thing doesn't have solutions. But now we can write this as minus 3 halves plus or minus root 47 over 2 times I, because we know the square root of minus 1 is I, so the square root of negative 47 is root 47I. And of course we have the 2 on the denominator there. So that's not such a big deal. If you had to factor the quadratic over the complex numbers, this cannot be factored over reals. That's as fact as it gets. But if you do it over complex numbers, you can have x minus 3 halves plus root 47 over 2i. So that is one solution. And then the other factor would be x minus 3 halves minus 47 over 2i. And if you like, you can simplify this to be x plus 3 halves minus root 47 over 2i, x plus 3 halves plus root 47 over 2i. So the idea being that if you expanded this out and simplified, you would just reduce to that. Okay, so there's not too much to this. Just use the quadratic formula as before, but realize the square root of negative something is I times the square root, as if it had no negative there. Okay, any questions about that? As I say, it's not too tricky. Here's something that is a little trickier. We're going to need to define what it means to take e to the z, where z is a complex number. This is sort of weird. E to the x we understand. We have a graph, no problem. In fact, if you write z is equal to x plus iy, then if there's any justice in the world, e to the z, which would be e to the x plus iy, should factor into e to the x times e to the iy, if exponential rules are still going to hold. Now this, we understand, x is just a real number, so this is just the regular old e to the x. The tricky thing is this, e to the iy. What on earth does that mean? Well, one way to find out what it means is to pretend that z is real and define e to the z to be the sum from n equals 0 to infinity of z to the n over n factorial. That should be a pretty familiar power series. If z is just a real number, this is exactly true, and it's true for all real numbers. We know this from our studies of Maclaurin series that we've just completed last week. Well, I don't really have the time or tools to go into what it means to converge for complex numbers. We need a slightly different theory of limits, but it's not really very different. We have absolute values, after all. That's really critical. I guess I don't feel so bad about it since we didn't really spend any time defining what a real limit actually was. That's in Appendix A of my book, by the way. You need epsilons and all that sort of stuff. So let's just take it as read that this object here makes sense, even if z is a complex number, and it converges to something, and we're going to call it e to the z. And then the beautiful thing is that you can prove, and I do this in section 28.1.1, not that you need to know it or anything like it in Math 104, but I prove that yes, e to the z, e to the w is indeed equal to e to the z plus w. So it's a reasonable thing. And so we can actually define what e to the iy means using this infinite series. Seems a bit contorted, but soon we'll see a much easier way to view it. Anyway, I kind of need to just throw that out there and say, look, we can now legitimately take complex exponentials. We don't know what they mean yet. So bear with me. I'm going to come back to them in a few minutes. But first, I need to tell you about the complex plane. Now, this is not esoteric by any means. This is critical. For real numbers, we have a line, right? X. We just plot a point on the line. For complex numbers, we have x plus iy. That's a typical complex number where x and y happen to be real. So we can't just use a line to plot it. We need a plane. So we define the complex plane. Now, it looks like a regular set of graph or axes, but then it's not supposed to be y as a function of x. Instead, we've just got these two things, x and y, and maybe we should even label this the real axis and this the imaginary axis. I don't know, maybe just r and I, or I don't know what to call it. I just don't want you to think of it as the normal x and y axes where y is f of x. It's not like that. We're not going to be plotting sine curves really on this at all. We may draw a circle though. In any case, the point is you can plot various points, such as the complex number 2 minus 3i. Well, where do you plot that? First of all, you take the real part, 2, and you take the imaginary part, minus 3. And you plot the point 2, comma, minus 3, and then this is not 2, comma, minus 3, but rather the complex number 2 minus 3i. In fact, this point here is not actually negative 3. It is negative 3i. That would be a better way to label it. So this point is like a point on the number line, but it's a point in the number plane. The complex numbers, as I said, are denoted by this bold C for complex. Let's plot some other points, or some other numbers. 2i would be up here, whereas minus 1 is here, and 2 is there. So you can plot complex points. All right. Well, it's nice. One point that is really nice to learn is that if you have two numbers, z and w, that anywhere in the complex plane, and you consider what I defined last time as the modulus, the absolute value if you prefer, but it's called the modulus in the complex number setting. That is a quantity. Just to remind you, if you have the real part of z is x, and the imaginary part is y, then the definition of the absolute value of the modulus is the square root of x squared plus y squared, inspired by Pythagoras' theorem. So this is actually the distance from z to the origin. Modulus of z, or mod z for short, is the distance from z to the origin. So z to the origin. And in more generality, mod z minus w, the modulus of z minus w, is the distance between z and w. So in particular, the most important curve I can draw in this complex plane is the circle of radius 1, so-called unit circle. And that has equation mod z equals 1. These are all the points whose distance from the origin is precisely 1. Unit circle. All right, so now we've got some idea of the geography of the plane. I'm going to switch coordinate systems on you and talk about polar coordinates. Now, question?
Yeah, the absolute value of the modulus of z equal to the square root of x squared plus y squared. Is that really a definitional thing? Or like
The question is this a definition or is this a theorem? Well, let's take it as the definition, and then notice that it means this, the distance from z to 0. Or if you prefer, you could define it as the distance from z to 0, and if you did that, you would use Pythagoras' theorem. You drop this down, this is x and this is y, and of course, this is root x squared plus y squared, and it also works if x and y are negative because the squares get rid of the negatives there. Another question? Yes. Well, okay, so for the modulus of z minus w, how do you represent that in terms of x and y? Well, you'd have to do something like, you'd know z is x plus iy, and let's say w happened to be a plus ib. Then the difference, z minus w, would be x minus a, there's the real part, plus y minus b. Right? I mean, you're just taking them away and grouping them. So, of course, the absolute value, or the modulus, rather, is the square root x minus a all squared plus y minus b all squared. And that's actually the distance formula from high school, the formula from x comma y to a comma b, formula for the distance between those 2 points, rather. So everything is just tied in. We haven't really done anything intrinsically complex right now, in a way. All right, so what I want to do, as I said, is switch to polar coordinates. Now, I didn't spend a lot of time on these videos talking about polar coordinates because they sort of, I don't know, they've been flip-flopping between Math 104 and Math 103, and kind of, I guess they're really more in Math 103 now, but it's been a little neglected lately. I'm not quite sure where it belongs. So let me just tell you what we need to know about it. Let me just sort of remind you about polar coordinates in general. What is a coordinate system anyway? It's just a way of describing points in the plane. I want you to think of yourself standing here in a field facing east, and someone says 3, 4. Right? Well, that's Cartesian. What it means is you walk 3 east and then 4 north, and you get to your point. You could actually walk 4 north and then 3 east. It would work too. And the convention is that if you have a negative, I still want you to think of being east, but you just go backwards. Or, for the y-coordinate, you still face north, but you walk backwards. Negative means backwards. Well, another way of describing it, imagine now that you're facing east as before, but instead of telling you how far I want you to walk this way and then this way, I say, rotate an angle of theta, where I tell you what that theta is. Say, 60 degrees. Pi over 3. This is going to be a different point. I say, rotate pi over 3, and then I tell you how far to walk. Walk 2 feet, 2 units. That's another way of describing that point. And in polar coordinates, we write it as 2 comma pi over 3, with the understanding, I'll put the little polar just to make sure, that we're going to write r comma theta in general. So that we're always going to put the theta, the angle you have to turn, second. And we'll put the distance you have to walk first. Even though, as I've described it, you really do the theta thing first, and then you walk. So in general, the point r comma theta consists of turning theta degrees, or theta radians rather, starting facing east along the positive x-axis. So this way you turn theta, and then you march forward r. Now, we're going to insist that r is a positive number here. When you do polar coordinates, it doesn't have to be. For complex numbers, r is going to be positive, so Let's not even think about walking backwards. Theta could still be negative, though. If theta is negative, you actually turn this way instead. All right. Now, that's a perfectly good way of describing a point in the plane. There are a couple of interesting points, though. First of all, if the point you want is actually the origin, then it doesn't matter what theta is. If r is 0, you can turn as much as you like. Okay, then go 0. Doesn't make a difference. So 0, comma anything is still the origin. Another degeneracy that's not quite as severe, or at least multiplicity, is that theta is not quite uniquely determined. You can always add 2 pi, or 4 pi, or 6 pi. Look, suppose I said, oh, turn pi over 3, and then walk 2. Well, how different would it be if I said, turn 2 pi plus pi over 3? That's 7 pi over 3. Well, that would mean I would turn 2 pi in place, and then another pi over 3, and then walk 2. Of course, I end up at the same point. You can add as many multiples of 2 pi as you like to theta, or subtract them. That just means you go backwards. It depends how sadistic you feel to, say, your poor friend who's taking orders from you. If you want to say, oh, turn 200 pi, well, and they just turn around 100 times, get really dizzy, and don't really accomplish anything. So, okay, that's the idea of polar coordinates in a nutshell. Now, why do we care about polar coordinates? Well, it's to do with this complex exponential stuff. So let's just talk about this for a little bit. Here is the big idea. There's an absolutely beautiful formula that I'm going to whip out that says this. E to the I theta, remember this is this weird thing we were looking at. I wrote before e to the I y, but here we have I theta. This is an imaginary exponent. That's a weird complex number. It's defined by a nasty series. If you really wanted to write it down, the series is e to the I theta is the sum of I theta quantity to the n over n factorial from n equals 0 to infinity. That doesn't really seem easy to work with. So what is the real part of e to the I theta? Well, it turns out that if you expand this, and it's a good little exercise, and you look at only the real part, you'll only get the even ends. Because all the odd ends will have i's in them. Remember, I squared, I to the 4th, I to the 6th, that just oscillates between 1 and minus 1. So it becomes alternating, and funnily enough, it becomes cosine theta. But if you only concentrate on the odd terms, you get, again, oscillating, but with an I out the front. And it turns out the imaginary part is sine theta. So you get this extraordinary formula just from the Taylor series, which deserves a proof, but I don't have time for it. Instead, look at the end of chapter 29 if you're curious, or just try to expand this out. And as I said, look at the even and odd terms separately, and you'll find you get the two series for these functions here. So this is a marvelous formula. What does it mean? What does it mean? Well, let's look at polar coordinates. Let's just take a point on the unit circle. Let's say I consider the polar coordinates 1, theta. That means you're going to turn theta here, and you're going to march up 1. So you'll end up at this point on the unit circle. Well, the x-coordinate is cosine theta, because the hypotenuse is 1. And the y-coordinate is sine theta. So if we were to consider this as the complex plane, this point here, z, has real part cosine theta and imaginary part sine theta, so it is cosine theta plus I sine theta. And by that tremendously marvelous formula, which is called Euler's formula, by the way, the E actually stands for Euler. By this formula, this is also the point e to the I theta. That's another way of writing the same point. So, in more generality then, we can just multiply by r. And all that will do is put us on a different circle, this time of radius r, without changing the angle. So basically, we end up with the following. r e to the I theta is r cosine theta plus I r sine theta. Well, that's obvious just by multiplying Euler's formula by r. But what it means is r e to the I theta is the point in the complex plane with polar coordinates r, comma, theta. Just as x plus iy is the point in the complex plane with Cartesian coordinates x, comma, y. So I've given you two different ways of writing a complex number, and they both correspond to some point in the plane, depending on whether it's x plus iy, in which case you use Cartesian coordinates, or r e to the I theta, in which case you use polar coordinates. Now, of course, as I said, there's more than one way to get to the point. You could use Cartesian coordinates, or you could use polar coordinates. And of course, you get the same number. If you get to the same point, you must have the same complex number. So I guess the point I'm trying to make is this. If a point in the plane has Cartesian coordinates x, y, and the same point has polar coordinates r, comma, theta, then the two complex numbers, x plus I, y, corresponding to the Cartesian coordinates, must equal r e to the I theta, the point, the polar form. So actually, we'll say this is in Cartesian form of the complex number. This is the polar form of the complex number. Okay, well, this is all pretty abstract. Everything is going to depend on converting between one to the other. And soon, we will see why it is so nice to be able to work in polar form. But you're just going to have to bear with me for a little bit. I don't have a lot of time about this sort of thing, but to get into this and jump the gun, but as I say, we will soon see the virtues of polar form. Now, what I'd like to do is talk a little bit about conversion from polar, or to and from polar form. So converting, this is very important, converting from polar to Cartesian. We'll start with that. I tend to think of Cartesian as being sort of like my native language, which is English, or Australian English if you prefer, and polar is in some foreign language which I don't speak very well, like, say, French. It's easier to translate from French to English for me than it is from English to French. So that's why I start with polar to Cartesian. It sort of seems to be easier. Look, to convert from polar to Cartesian, you have the geometry of it is quite simple. The distance is r, and the angle is theta. So the x-coordinate is r cosine theta, and the y-coordinate is r sine theta. And guess what? The conversion, I need to know, given r and theta, I just need to find these quantities. But that's actually the formula I wrote before. Namely, r e to the I theta is r cosine theta plus I r sine theta. So that's Euler's formula multiplied by r. You might as well learn it in that form. When r equals 1, we get exactly Euler's formula that I had written before with a box around it. Okay, so what does this mean? Well, if you'd like to convert something like, I give you a complex number, 2e to the I 5 pi over 6. That's a legitimate complex number, and I ask you, what is the real part of it? What is the imaginary part? What is its Cartesian form, basically? Well, whip out the formula. This is 2 cosine 5 pi over 6 plus I sine 5 pi over 6. Let's just draw a graph of it. Well, it's not really a graph, it's a plot. Plotted on the complex plane, 5 pi over 6 is here. It's not quite all the way to pi. And a distance of 2 up there. So this is the point we're looking for. Well, of course, cosine 5 pi over 6, the reference angle is pi over 6. Cosine pi over 6 is... Do you know the answer, or are you just... Oh, I left out the 2. Thank you. You are quite right. I2 sine. Okay, so cosine 5 pi over 6. What's cosine pi over 6? Root 3 over 2. And it's negative because we're in the second quadrant. So minus 2 root 3 over 2. Whereas sine pi over 6 is a half. And second quadrant, sine is positive. So I get negative 2 root 3 over 2 plus I times 2 times a half. So this is just negative root 3 plus I. And if you look at the picture above, it looks totally plausible that this should be negative root 3 and this should be I here. It's minus root 3 comma 1. That's the point. Okay, so that conversion from polar to Cartesian is no more tricky than knowing the formula and being able to take trig functions. So you need to know your trig. Once again, I've been saying it all along. Know how to take trig functions of common angles. All right. Any questions about converting from polar to Cartesian? Well, in that case, we move on to converting Cartesian to polar, a little bit more difficult. So we start off with the complex number z equals x plus I y, and we'd like to write it in the form r e to the I theta. So we'd like to convert it that way. Well, before we had formula. Here it's not quite as nice. Basically, we're looking at the point x plus I y. X comma y is over here. And this distance is r. Well, clearly r is going to be the square root of x squared plus y squared. No problem there. What about theta? Well, theta does sit in this triangle, so you do have tan of theta is y over x. That's true. There's two problems, though, with this formula. First of all, it doesn't work if x is 0. If x is 0, you sort of get tan theta is infinite, or minus infinity. Sure, it has to be pi over 2 or 3 pi over 2 or something like that. So that's not such a big problem. The real problem is that you cannot tell which quadrant it is in just if you know tan theta. For example, suppose that we take the point minus 1 minus I and try to convert that. I'm going to use these two formulas. Okay, if I just do, I find r is the square root of minus 1 squared plus minus 1 squared. I just should say that I'm thinking of this as minus 1 plus minus 1 times I. So the real and imaginary parts are both negative 1. So r is clearly root 2. As for theta, tan theta is y over x, which is minus 1 over minus 1, which is 1. So tan theta is 1. What is theta? What number has a tan of 1? Pi over 4. So maybe you think theta has to be pi over 4. Well, it could be 5 pi over 4. That's another number. That's in the third quadrant. Well, which one is it? If we just plot the point you get minus 1 minus I. The point is clearly in the third quadrant. This angle cannot possibly be pi over 4. Not true in this case. 5 pi over 4 is the one we want. So that's why I say you have to be careful. In fact, I would go so far as to say you should always draw a diagram. Just little sketch. That's all you need, just to see where you are, which quadrant you're in. Get some sort of orientation going on. Anyway, let's finish off this problem. We have seen that minus 1 minus I has r is root 2, and theta is 5 pi over 4. So we package it up like this. R e to the I theta. So we have successfully converted negative 1 minus, well, minus 1 minus I, that's how I'll say it, into root 2 e to the I 5 pi over 4. These are the same complex number. This one looks a little simpler. So you might, again, wonder why on earth we want to write something in such a complicated way. But this will soon become clear, as I said. All right. So that's the basic idea. Just use this formula. There are a few special points I would like to look at, though. Suppose I look at, say, the point 4. Well, that's not a problem. 4 is 4 e to the I 0, which is just 4. E to the 0 is 1. So there's nothing special there. Actually, but I'm kind of jumping the gun. Hold on to that thought for a second. There's one more thing I need to say. 5 pi over 4 is not the only possible answer. We could add 2 pi to that. So 5 pi over 4 plus 2 pi is 13 pi over 4 if you work it out. After all, 2 pi is 8 pi over 4, and 5 plus 8 is 13. So you could actually write this as root 2 e to the I 13 pi over 4. That's got to be the same complex number, because instead of just rotating 5 pi over 4, this 13 pi over 4, again, means you go all the way around and then 5 pi over 4, and of course you get to the same point. You could have subtracted instead. 5 pi over 4 could give you, if you subtract 2 pi, you get negative 3 pi over 4. That's again the same point. So instead of facing this way and turning 5 pi over 4, I should have been turning all the way over here, sorry. I could turn this way, not as much, and I would be facing the same direction. Of course, you could do 21 pi over 4, 29 pi over 4. Just add any 8 to that 13, or any multiple of 8. 8 pi over 4 in total is 2 pi, and you will get the same point. Or you could subtract any multiple of 8, and you get the same point. So there's no uniqueness here. Normally what we try to do is pick a theta between 0 and 2 pi. That's the simplest thing to do. Sometimes between minus pi and pi. But you don't want it to be 13 pi over 4 if you can avoid it, because 5 fourths is easier to deal with than 13 fourths. Minus 3 fourths, pretty good too. Either of those are acceptable. All right, so now back to this. 4 is easy. The polar form, the theta is just 0. After all, you don't have to turn. If you want to get there to 4, you just go. You don't have to turn. There is another way of writing it, of course. 4 e to the I times 2 pi is also 4. After all, you just turn around 2 pi and walk 4, and you end up in the same place. Now that I think about it from your perspective, all my walking should have probably been done this way. That's the positive x-axis. Whoops. Can we take this video and do a mirror image shift? If we did that, the walking would be right, but I guess you wouldn't be able to read the writing. Oh well, screw it either way. Anyway, sorry about that. All right, so anyway, never mind this. You guys have got a good sense of perspective, and I'm sure you'll work it out. Now, as I said, 2 pi, same as 0. It's far as we're concerned. In fact, e to the I 2 pi is 1, and so is e to the I 4 pi, 6 pi, 8 pi, etc. Any multiple of 2 pi. E to the I 2n pi, or 2 pi n, is 1 for any integer n. Even a negative one. E to the minus 2 pi I is 1 too. Is 1 as well. All right. How about negative 1? You might be tempted to think that negative 1 is just negative 1 in polar form, but it's not. You've got to walk a positive amount. So you start facing this way, you have to turn 180 degrees, pi, and then march 1. We don't even need these formulas for tan theta. We can just see it on the picture that it should be 1 e to the I pi is the angle that we turn. And so another way of writing this is that e to the I pi is negative 1. That is a beautiful formula. I could rhapsodize about it for quite a while. It's a special case of Euler's formula with the theta is pi. And if you take that previous formula that's still in the box up there and substitute theta is pi, you will find this. Now, why is this so nice? One, because it looks ridiculous. I mean, who would have thunk it? It's true. But I kind of think that, hey, look at these 4 things you've got here. First of all, you see pi when you're a kid, you know, circles, ratio of circumference to diameter. Circles are pretty fundamental in the universe, apparently. Negative 1 is a big step forward as well for humanity. Dealing with negative numbers meant that people could work out how to get out of debt, hopefully, or at least what it meant to be in debt. And then more exotically, we saw E to do with compound interest and this sort of continuous time compounding. And then finally I, the square root of negative 1. And somehow they're all bound up in that formula there. In any case, what this means is that negative 1, the Cartesian form, has polar form e to the I pi. So that fancy equation is just the polar to Cartesian transformation of the number negative 1. Of course, negative 6 is 6 e to the I pi. This is not polar form. This is polar. A couple more, and then I'll do something useful with polar form. We'll find that rarely are the questions in Math 104 at least going to be convert this number to polar form. They will be instead questions like the ones we'll consider in just a few minutes. And then along the way we're going to have to be able to convert. So this is more of a tool than an end in itself. I keep promising that you'll see why they're so useful. I'm almost ready to tell you. But first, I just have a couple more points I would like to transform. Here's one. What's the point I in polar form? Well, let's look at where it is. You never have to, you never have to wonder about this. You just have to plot the point and say, okay, if I was facing this way, how would I get to this point I? Well, I would have to turn pi over 2, and then I would have to walk 1. Of course, I could turn instead minus 3 pi over 2, or I could turn an extra 2 pi. I've already talked about this. If I do the simple thing, I get pi over 2, and I get 1. And so I is just 1 e to the I pi over 2. Or in other words, you can leave out the 1 since it's a product. I is itself e to the I pi over 2. And for some reason, people have a lot of trouble with this. More even than minus 1 is e to the I pi, the previous formula. I guess it's because the I appears up there, and you might wonder why on earth you need all this e to the pi over 2 crap when you've got the I there. But nevertheless, this is Cartesian, 0 plus I, and this is polar. By a similar token, if we do minus 5i, well, we'd have to go 3 pi over 2 around and then walk 5. So we turn 3 pi over 2 and then we walk 5. So this is 5e to the I 3 pi over 2. Perhaps more efficient would be to turn the other way pi over 2, which is really negative pi over 2. And so another way of writing this is 5e to the negative I pi over 2, or I minus times minus pi over 2. And of course, again, you can add multiples of 2 pi. In fact, if you add 2 pi to negative pi over 2, you do get the 3 pi over 2. You could have 7 pi over 2. You could have 11 pi over 2, etc., etc. All right, so those are sort of special cases of the polar to Cartesian form. Those are the ones, I've looked at ones which are on the coordinate axes. If it's on the coordinate axes, you've got to draw a picture. These tan formulas really get confusing. If it's not on the coordinate axis, you should just draw a picture like we did in the first example. All right, so that's the idea about conversion between polar and Cartesian. Does anyone have any questions before we go on to some nice applications? All right, well, in that case, the first thing that I consider an application is just to notice that multiplication, which was real nasty in Cartesian form, right? You had a plus ib times x plus iy, and you have to multiply all the terms out. Multiplication is nice in polar form. So is division. Multiplication and division. Here's an example. Suppose I have two complex numbers that are in polar form. And I have 3e to the I pi over 4. Say that's one number. And I'd like to multiply by the number 2e to the minus I 3 pi over 8. Okay, so those are two complex numbers in polar form. Well, you just use the exponential rules. You have 6e to the I, and you just have to add these exponentials. Pi over 4 minus 3 pi over 8. So this is 6e to the I times minus pi over 8. And I don't say what that is, I'm just going to leave that in polar form. So multiplication is really quite straightforward. Now, what about taking a large power instead? So suppose I do 3e to the I pi over 4 again, and I want to raise that to the 200th power. What would that be? Well, I just raise 3 to the 200th power, and I multiply these exponents. So I get e to the I pi over 4 times 200. This is, of course, the same as 3 to the 200 times e to the I 50 pi. Could we simplify that? What's e to the I 50 pi? Can anyone say what it is? What's e to the I 2 pi? Not 0. Exponentials are never 0. 2 pi is the same as 0, so it's like e to the 0. So it is, this quantity is 1. Yes, 50 pi is like 25 lots of 2 pi. You're standing there and you're turning around 25 times. You're still pointing the same direction. Yes, this is just equal to 1, so the whole thing is 3 to the 200. So we start with a complex number, raise it to the 200th power, and guess what? We get a real number. Well, that's not so surprising. After all, if you start with I and you square it, you get minus 1. All right, so taking powers is very nice in polar coordinates, which means that if you do want to take a power of a large number, such as 1 minus I to the 99, suppose you wanted to compute that. Well, if you're going to do this, you would be absolutely nuts to use the binomial theorem here. You know, 1 minus I, 1 minus I, 1 minus I. 99 copies of this. You just don't do that. What you have to do is convert this to polar first, and then we can take the large power. So convert 1 minus I in polar is what? Well, we apply our conversion technique. What I'm going to do is I'm going to plot the point 1, minus I. And it's down here in the fourth quadrant. Okay, so what's this angle here? Well, you could use the tan formula and whatever. I mean, the thing is, I just like to use the geometry. This is a 1, 1, root 2 triangle, and this is pi over 4 here. So this must be 7 pi over 4. You can just see it, that the angle is 7 pi over 4. So it's root 2 e to the I 7 pi over 4. By all means, use the formulas if you prefer. You should get the same answer. You could also write, and it would be completely legitimate to write this, e to the minus I pi over 4. But I'm going to solve the problem using this. I like to work between 0 and 2 pi. It's just personal prejudice. It doesn't really matter. A lot of mathematicians always between minus pi and pi. That's fine. That's symmetric. It's nice too. I don't care. Either one should work if you do it properly. So anyway, we have 1 minus I is equal to root 2 e to the I 7 pi over 4. This means that if we take 99th powers of both sides, 1 minus I to the 99 is root 2 e to the I 7 pi over 4 to the 99. And I guess I'll write the root 2 as 2 to the half, just to be pretty about it. So I get that expression there. So this is equal to 2 to the 99 over 2 times e to the I 7 pi over 4 times 99. Well, I guess we've got to do a little bit of work. What's 7 99s? Well, 700s would be 700, right? So 693. This is how you can save time. Little considerations like that. 2 to the 99 over 2. E to the I 693 pi over 4. And that's surely the answer. That is the answer. But it's kind of, well, not cheating. It's sort of begging a certain question. You see, we started with 1 minus I, which is in Cartesian form. And we really ought to give the answer in Cartesian form. There it is in polar form, not Cartesian form. In fact, when I say we really ought to, it depends where your obligations lie. Let's just be realistic here. Math 104 final question says, express your answer in Cartesian form. So you better do it if you want full credit. This is nice, but it's not as nice as it should be. First of all, we should cut down the 693 over 4 to size. We've got to cut it down because we've got to be able to take the cosine and the sine of it. So what we've got to do is work out how many 2 pi's to take away from it in order to get it down to a number between 0 and 2 pi. So the way I'm going to do this is I'm actually going to do the division. 4 into 693. Well, 4 into 6 is 1. 4 into 29 is 7. Remainder 1. 4 into 13 is 3. And the remainder is 1. So what have we got? We've got 693 over 4 is 173 and a quarter. Now I'm going to do something that you never really would have done in elementary school, which is to say that I'd rather write this as 172 and 5 quarters. I'm going to borrow 1 away from the 173 and stick it on the 1 quarter. That's a little bit unorthodox. Why am I doing that? What's good about 172 that was not good about 173? Anyone tell me? It's even, yes. It's divisible by 2. So what I'm going to do is just as a sidebar over here, I'm just going to notice that e to the I 693 pi over 4 is the same as e to the I 5 pi over 4 plus 172 pi. And when you look at that 172 pi, it doesn't matter, because it's an even multiple of pi. As it turns out, it's like, 86 times around. But it doesn't matter how many times around it is. If you've got an even multiple, it goes away. So this is just e to the I 5 pi over 4. Okay, so the cutting down to size, you just take a fraction as it is, write it like this, and if it's even, you're already done. If I'd gotten 172 and a quarter, I wouldn't have done this extra trick. But I really want an even number plus the remainder. So if necessary, I'll borrow 1 away. That's just a good little technique there. It's a bit unusual, so you've got to get this in your skull that this could be required. Anyway, so from all this, I can simplify this a little as 2 to the 99 over 2 times e to the I 5 pi over 4. Okay, already it's still in polar form, but already it's nicer. This is a nicer solution. It's easier to understand in polar form. But nevertheless, I said we are supposed to convert it to Cartesian form, so I'm going to use Euler's formula. The 2 to the 99 over 2 is just a factor, so it's going to be cosine 5 pi over 4 plus I 2 to the 99 over 2 sine 5 pi over 4. That's how you deal with e to the I theta. Cosine theta plus I sine theta. And there's the factor, 2 to the 99 over 2. So we just have to be able to take cosine 5 pi over 4 and sine 5 pi over 4. Well, 5 pi over 4 actually puts us in the third quadrant, so they're both going to be negative. They're both, in fact, going to be negative 1 over root 2. So this is 2 to the 99 over 2 times negative 1 over root 2 plus I times 2 to the 99 over 2 times negative 1 over root 2. Actually, you can be more elegant about it. 1 over root 2 is actually 2 to the minus a half. So you take off minus a half from 99 over 2, you get 98 over 2, which is just 2 to the 49. So if you think about it, you can take out a factor of negative 2 to the 49, 1 plus I. And that is the Cartesian form. If you really want to write it out, the real part is minus 2 to the 49, and the imaginary part is also minus 2 to the 49. Pretty big number, that. So minus 2 to the 49 plus minus 2 to the 49, I. So that's how you take large powers of complex numbers. You convert the number you want to take a large power to into polar form. You take the power, you do the stripping down with this odd trick to even if you need to, and then you use Euler's formula and convert it back to Cartesian form, simplifying if necessary. These things need to be practiced. That's just one example. There's nothing different about other examples. They all involve the same techniques, but you just need to practice them. But you know that by now. These things, at least in Math 104, seem to come up a lot. By the way, a slight disguise would be if the question just said, what is the real part of this? So I guess go back to here. The question could just say, what's the real part of 1 minus I to the 99? It doesn't say simplify this in Cartesian coordinates, but you have to do exactly the same thing. And then, of course, once you've got it down to the Cartesian form, you can just read out that the real part is negative 2 to the 49. All right? So that is one class of problems where polar coordinates really shines, taking large powers, as I said, of complex numbers. So now I move on to another topic, but first, does anyone have any questions about that particular type of problem? All right. Let's move on to the main type of problem. Solving equations that look like this. Solve z to the n equals w, where n is a certain integer and w is given. For example, suppose I want to solve something like z to the 5th equals negative root 3 plus I. So what are the solutions to that equation? Well, we could write z is the fifth root of negative root 3 plus I. And that doesn't really tell us very much. For one thing, it doesn't tell me what the real part or imaginary part is. It doesn't even tell me how many solutions there are. After all, if I take the square root of, say, 4, I get 2 solutions, 2 or minus 2. So this is sort of lame. Screw that. So what I'm going to do is I'm going to show you how to do it step by step, and then maybe I'll reiterate what the steps are and use it to do a different example of the same type of problem. So again, polar form all around. So the first thing to remember, yes, polar. So what do I need for polar? Well, I've got two quantities. Z is unknown, and I've also got this quantity minus root 3 plus I. So let's convert both sides to polar. For Z, there's not much conversion. I'm just going to define it to be r e to the I theta, where r and theta are unknowns. If I can find r and theta, I will know what z is, at least in polar form. But I've also got to convert minus root 3 plus I into Cartesian, into polar form from Cartesian. So let's just draw it. It's minus root 3 plus I. There it is. So I think we already even saw something like this. It's a triangle of root 3 and 1. So 1 plus 3 is 4, squared is 2. And this reference angle, let's call it, I don't know, phi. Tan phi is 1 over root 3. So phi is 30 degrees, pi over 6. And therefore this is 5 pi over 6. So it's got an r of 2 and an angle of 5 pi over 6. Therefore minus root 3 plus I is 2e to the I 5 pi over 6. All right, so everything is in polar form. Let's now assemble these things and put them into the equation. So z to the fifth becomes re to the I theta, quantity to the fifth, and root 3 plus I in polar form is 2e to the I 5 pi over 6. No problem. Well, here's where the polar shines again. We take the fifth power, and we get r to the fifth, e to the I 5 theta is equal to 2e to the I 5 pi over 6. Is everything clear so far? That makes some sort of sense, right? We've just converted the original equation into polar form on both sides and expanded. Now here comes the nice thing. If I take modulus of both sides, e to the I anything has absolute value of modulus 1. So both sides, this goes away, and we can really separate this equation into two pieces. We can equate the modulus and then the argument part. This is called argument. So anyway, we get r to the 5 equals 2, and we get e to the I 5 theta equals e to the I 5 pi over 6. So it breaks up into two, which is great because we need to find both r and theta. A question?
Yeah, what was the reasoning behind being able to break up?
Why could you break it up? Okay, a review of the reason is that if this is true, we can take modulus of both sides. Right? So if we take the modulus, let me just point out that the modulus of, say, r e to the I phi is r. In polar form, r is the modulus. Right? It's the distance from 0 to the point, by definition. So in particular, the modulus of the left-hand side here is r to the fifth, and the modulus of the right-hand side is 2. And since these are the same complex number, they must have the same modulus. So r to the fifth must be 2. So So once you've got that, you can divide this equation by this equation to get this. That's the justification. All right. R to the fifth equals 2. Why can't I just write R is the fifth root of 2? Or if you prefer, 2 to the fifth. I thought I wasn't allowed to take fifth roots. Well, the difference is here, R is a positive number. It's a real number. It's not a complex number. Real numbers have only one positive nth root. So that's the one we're going to take. On the other hand, here it is tremendously tempting to write 5 theta is 5 pi over 6. It's really, really tempting to get rid of the e to the I. Sort of take a logarithm and cancel the i's. But it's not true. We need to add in a 2 pi n. And the reason can be summarized in the following principle. If e to the I A, capital A, equals e to the I, capital B, where I don't say what A and B are, only that they're real, then A equals B plus 2 pi. Actually, I'll use a k instead. I think that's what I did in my book. Let me change this n to a k. K, an integer. It doesn't matter what you call it as long as you know it's an integer. Okay, A is not B. A could be B, or it could be B plus 2 pi, or B plus 4 pi, and so on. Right? We've discussed this before. For example, e to the I 2 pi is the same as e to the I 0, but 2 pi is not the same as 0. If two numbers have the same, or two different representations in polar coordinates, you do not know that the angles are the same. You know that they differ by a multiple of 2 pi. Remember, you just do that turnaround thing. Now that is such an important principle that not only am I going to put one box around it, I'm going to put 2 boxes around it, and because I think it's really even more important than that, I will put 3 boxes around it. And I will call it the triple boxed principle whenever I need to. So that there's nothing else with 3 boxes. Actually, this is not necessarily the most important thing in the course, but somehow it's just so easy to forget that I feel like when you're looking at this equation here and you say e to the I 5 theta equals e to the I 5 pi over 6, oh yeah, 5 theta is 5 pi over 6. No, triple box principle plus 2 pi k. All right. So, given that, we can operate properly by dividing by 5. Theta is pi over 6 plus 2 pi over 5k, where k is an integer. So now we have found r, it's just the fifth root of 2, and we have found not just one value of theta, but apparently infinitely many values of theta. Now here's the second little trick or insight, is that we only need 5 values of k, which I'm going to take 0, 1, 2, 3, and 4. 5 values. Why 5? Because the initial equation is degree 5. Z to the 5 equals something, minus root 3 plus I. There can be at most 5 solutions. So we will find that these are the 5 values that will do. Or these are 5 values that will do. And that any more, and we'll just keep repeating ourselves. Why will we find that? Well, let's just see. We know that r is always the fifth root of 2, which I'll write as 2 to the 5th. But theta is what? Well, it can be pi over 6. But when we have k equals 1, it's pi over 6 plus 2 pi over 5. And we really ought to take a common denominator. So that's 5/30ths plus 12/30ths, which is 17 pi over 30. It could also be pi over 6 plus 4 pi over 5, which is, well, we're just adding 2/5 pi every time, I guess. So the next one is going to be 29 pi over 30. Pi over 6 plus 6 pi over 5 will lead to 41 pi over 30. And finally, pi over 6 plus 8 pi over 5 is 53 pi over 30. All right, so basically I'll come over here. Let's just rewrite those values of theta because it's a bit of a mess there. Pi over 6, 17 pi over 30, 29 pi over 30, 41 pi over 30, and 53 pi over 30. Those are 5 different values of theta. Now, what's z? That's what we're supposed to find out. These are long problems, but we're right at the end of it. Z is r e to the I theta. So we're going to have 5 solutions. The first is 2 to the 5th e to the I pi over 6. The second is 2 to the 5th e to the I 17 pi over 30. And so on. You should write out all 5. I'll write out, there's one more here, there's one there, and then 2 to the 5th e to the I 53 pi over 30 is the 5th solution. What a yuck. But there it is. Now, those are the solutions in polar coordinates. We really ought to convert them to Cartesian, and you have to do them one at a time. Unfortunately, most of them are nasty, or maybe fortunately. The first one is not. It's cosine pi over 6 plus I sine pi over 6. The next one would be 2 to the 1/5 cosine 17 pi over 30 plus I sine 17 pi over 30, and so on. You write out the other 3. Now, we don't know what cosine 17 pi over 30 is. You can work it out, but it's a pain. And it's certainly not relevant. But this one you should really convert to root 3 over 2 plus I times 1/2. You really should do that one. Because you know what cosine pi over 6 is, and you know what sine pi over 6 is. The others, you need to write out all 5 of them in that Cartesian form. And my hand is getting tired, so I won't do it. But it's in the book anyway. Now, before I see if there are any questions, I need to show you why those are the only 5 solutions, or in particular, why can't k be 5, 6, 7, all that sort of stuff, negative. And at the same time, I want to plot the solutions in the complex plane so we can see where the 5th roots of this number, root 3 plus I, actually lie. All right, let's just plot a diagram here. All 5 solutions have r equals 2 to the 5th. So I take a circle of radius 2 to the 5th. This is not the unit circle. It's the 2 to the 5th circle. The first solution is pi over 6. So there's the first solution. This corresponds, well, here's pi over 6. This corresponds to k equals 0 in my formula for theta. The next one, k equals 1, we have to add 2 pi over 5 to it. And we got the answer 17 pi over 30, which is somewhere around here. But the interesting thing is not that it's 17 pi over 30. The interesting thing is that it's 2 pi over 5 around from the previous solution. And so here is the solution of k equals 1. That's the solution, 2 to the 1/5 e to the I 17 pi over 5. To get the next solution, which was e to the I 29 pi over 30, you add an extra 2 pi over 5. And that's k equals 2. And then to get to the next one, which was 41 pi over 30, you add another 2 pi over 5. And then k equals 4, you add another 2 pi over 5. So the points actually lie on a regular pentagon. The roots lie on a regular pentagon. And this is nice, and it also shows us why k equals 5 will just take us back to the first point. If you do plug k equals 5, remember we had the formula theta is pi over 6 plus 2 pi k. K equals 5 gives us theta is pi over 6, 2 pi over 5 rather. So k equals 5, theta is pi over 6 plus 2 pi. So it's the same as pi over 6, it's just an extra 2 pi around. You get the same solution when you take e to the I theta. It's the same solution. Put a 2 to the 5th out the front. So k equals 5 gets you to here. K equals 6 gets you there. K equals 7, 8, 9, 10, 11, 12, etc. What about k equals minus 1? Well, then you just go backwards. So you're getting no extra solutions. You're getting different values of theta, but you're not getting different values of z. We have found the 5 values of z, and they would be written on the board if I had been bothered to write them all out. All right. Long and involved problems, but they're on at least every second Math 104 final. Does anyone have any questions about the method, or that, in particular, that example? No questions? A question.
Does the fifth root always create a regular pentagon, fourth root create like
A square, yes. The fifth root gives you a regular pentagon. The fourth root should be a square. Cube root would be an equilateral triangle. Sixth root, hexagon, regular hexagon, that sort of thing. Now, here's another example. Find the cube roots of I. There's the example. I'm going to do the same technique, but in faster motion. Well, I don't need to spend so long about the triple boxed, anything like that. So find cube roots of I. We're trying to solve the equation. You've got to be careful about writing IE, since I and E are both pretty important. Let's just say that is z cubed is I. Okay, what's the first thing we do? Convert to polar. Z is r e to the I theta. We don't know what r and theta are. We have to also convert I. And from what I said before, you just draw a little diagram. Pi over 2 is the angle here. So I is 1 e to the I pi over 2. Don't forget that. So in polar form, this equation becomes r e to the I theta, all cubed, equals 1 e to the I pi over 2. You will not be able to solve it if you do not convert that I into 1 e to the I pi over 2. This becomes r cubed e to the I 3 theta is 1 e to the I pi over 2. So we split up by taking modulus into r cubed equals 1, and e to the I 3 theta is e to the I pi over 2. Solution to this is r equals 1. Don't forget, 1 does have 3 complex cube roots, as it turns out, but r is not complex. R is just a positive real number, so the cube root of 1 is just 1. And then in this case, 3 theta is pi over 2, right? Right? Yes, the triple box thing. Look, e to the I something, e to the I something. You need that 2 pi k. K an integer. So in particular, theta is pi over 6 plus 2 pi over 3 k. Now what k's do we need here? How many different k's do we need? 3, because we start off with a cubic. Z cubed is I. So we only need k equals 0, 1, 2. Those are the only 3 values that we need. So we have theta is pi over 6, that's k equals 0. Pi over 6 plus 2 pi over 3, which works out to be 1 plus 4, which is 5 pi over 6. Or k equals 2 is pi over 6 plus 4 pi over 3, which is 9 pi over 6, otherwise known as 3 pi over 2. All right. These are the three solutions, or at least those are the three values of z. So moving over here, because I have more room, we know z is r e to the I theta. R is 1 in every case, so it's 1 e to the I pi over 6, 1 e to the I 5 pi over 6, or 1 e to the I 3 pi over 2. Let's convert each and every one of those three into polar coordinates. So the first, into Cartesian coordinates. The first one is cosine pi over 6 plus I sine pi over 6. The second is cosine 5 pi over 6 plus I sine 5 pi over 6. And the third is cosine 3 pi over 2 plus I sine 3 pi over 2. And now we do our trig. Cosine pi over 6 is root 3 over 2. Sine pi over 6 is a half, so we get root 3 over 2 plus I 1/2. Cosine 5 pi over 6 is the same but negative, root 3 over 2, whereas the sine is unaffected. What's cosine 3 pi over 2? Well, cosine 3 pi over 2 is 0. Sine 3 pi over 2 is minus 1. So this is just minus I. And there are our three solutions. Root 3 over 2 plus I times a half, minus root 3 over 2 plus I times a half, and negative I. And if I plot these on a diagram over here, I get root 3 over 2 plus I a half is here. Minus root 3 over 2 plus I times a half is here. And minus I is down here. And sure enough, it's an equilateral triangle. Actually, minus I, we almost should have guessed. That's a cube root of I. Let's just check that. Minus I cubed is minus 1 cubed times I cubed, which is I squared times I. Minus 1 cubed is minus 1. I squared is minus 1. And so we just get I. Oh yeah, minus I cubed is I. So minus I is a cube root of I. But we didn't need to memorize that or intuit it. It all popped out of that anyway. So that's the end of the solution. We've got the Cartesian form of the three solutions. And just for good measure, we plotted them and saw that, yes, they do lie on a circle of radius 1, centered at the origin, and they are an equilateral triangle. Any questions about that? So you obviously got to practice, as usual, these sorts of problems. That's the sort of big kahuna as far as this course is concerned. This is the sort of hardest problem that we want to ask you normally. On the other hand, there are actually a few variations that I'd like to cover before I move on to differential equations. Because we're getting so close to the end of the semester, I kind of have to push forward a little bit. I've only got 2 hours after this one to do all of differential equations. I think I need a little more than 2 hours. So. The answer is yes. The answer is yes, but since the question is not relevant to anyone watching on the video, I won't repeat it. Not that it's dirty or anything. It's a reasonable question. But anyway, here are just a few variations. I'll just take about 10 minutes to show. Suppose I asked you to solve z minus 2 all cubed equals I. What would you do then? You could expand it, but that would kind of be silly. Instead, make a substitution. Let capital Z be little z minus 2. So that capital Z cubed is I. And I've now reduced it into the standard form. Now, I'm not going to bother doing it again. I already know the solutions are we found that the solutions are z is, say, root 3 over 2 plus I times a half minus root 3 over 2 plus I times a half and minus I. And of course, this is equal to little z minus 2. So to find little z, you just add 2 to all these solutions. So z is 2 plus root 3 over 2 plus I times a half. 2 minus root 3 over 2 plus I times a half, and 2 minus I. Nothing to that. It's sort of silly. Okay, something a little bit trickier is to solve a quadratic equation with complex coefficients. So here's another example. Suppose I have a quadratic equation z squared plus 1 over root 2 z minus root 3I over 8 equals 0. Okay, solve that. Well, it is a quadratic equation, so we can use the quadratic formula. Let's see what happens. Z equals minus b plus or minus the square root of b squared, which is a half, minus 4ac. Well, it's going to be plus 4 times root 3 over 8, which is root 3 over 2, but there's also an I there. That doesn't get squared, it's just 4ac. And it's all that over 2. Well, guess what? In order to find this, we have to find the square root of the complex number 1/2 plus root 3 over 2I. So we need to find, before we can finish the problem, we need to find the square root of 1/2 plus root 3 over 2I. That means we need to solve the equation. I need a different number. Say, I don't know, w squared is 1/2 plus root 3 over 2I. So you need to launch into the full shebang. You let w equal r e to the I theta. You convert this into polar form, and I don't really have time to do it. But there are only 2 solutions. And they must be plus or minus of each other. So I'm going to leave it to you, or you can read it in section 28.4.1, but you should really try it for yourself to follow that same method and find that w is equal to itself root 3 over 2 plus I times a half, plus or minus this. So if you square this, you get this. It looks almost the same. But actually the real part and the imaginary part are switched around. So the solution to here will be minus 1 over root 2 plus or minus the square root, root 3 over 2 plus I times 1/2, all that over 2, which you should really write as minus 1 over 2 root 2 plus or minus root 3 over 4 plus I times 1/4. And you could write this out as 2 different solutions and write down the real parts and imaginary parts. So the real point is that you ended up with a square root of a complex number. And you have to understand that this means that you're trying to solve, I used w because the original problem had a z, w squared equals something, and it's just like the other problems. We've got the technique for doing that. We use polar coordinates, yada, 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 just as we did in the previous 2 examples. Any questions about that example? Well, a really tricky thing, the last variation, perhaps the trickiest thing, is to solve something of higher degree, like this. Z to the 4th, what do I want? I guess that's what I want. Z to the 4th minus z squared plus 1. I really thought I had a 3. No, I guess that's what it is. Solve that, equals 0. Well, how do I do this? The first thing to note is that it's a quartic, which is sort of difficult. However, it's really a quadratic, because you can write capital Z is little z squared. And so this equation becomes capital Z squared, little z to the fourth is capital Z squared, minus capital Z plus 1 equals 0. So I use the quadratic formula here. I get capital Z is minus b plus or minus the square root of b squared is 1 minus 4ac negative 3. So I get 1/2 plus or minus I root 3 over 2. And that's capital Z. And I want to remind you, this is the same as little z squared. So I'm trying to find little z. I have proved using the quadratic formula that little z squared is either 1/2 plus I root 3 over 2. So this means z squared equals 1/2 plus I root 3 over 2. Or 1/2 minus I root 3 over 2. Well, let's say z squared equals. So you find yourself in the rather sad position of needing to solve two of these problems. Again, I have to leave the details to you, but you know the first problem is actually exactly the same as the one we just did with up here. I didn't actually do it, but we found here that z is plus or minus root 3 over 2 plus I times 1/2. And I leave it to you to do the details and find that here z is plus or minus root 3 over 2 minus I times 1/2. And those are all the solutions. There are 4 solutions because the original equation is a quartic, degree 4 up here. Z to the 4th minus z squared plus 1 equals 0. So we found 4 solutions over here. Now, before I move on to differential equations, I want to just say, suppose I would like you to factor z to the 4th minus z squared plus 1 over complex numbers. Factor it now. Well, this is not so bad because we have 4 solutions. We know what they are. And to factor it, you just take z minus each solution. So one solution will be z minus root 3 over 2 plus I times 1/2. That's this solution up here with the plus. Now let's use the same solution with the minus over here, and we'll have z minus root 3 over 2 minus I times 1/2. That's from the first pair. The second pair, I get z minus root 3 over 2 minus I times 1/2. And finally, the last factor is z minus root 3 over 2. It's actually negative root 3 over 2 plus I times 1/2. So if you stare at these 4 solutions that we got up here, they appear in the 4 factors down there. And sure, you could take away some of these minuses and simplify it, but actually, what I'd like to do is show you that you could do something clever and group these two together, this one and this one, and multiply them out and get something really nice. What are we going to get? I'll just squish it in here. Suppose I take these two. After all, root 3 over 2 plus I times 1/2 is a conjugate of root 3 over 2 minus I times 1/2. In general, if I have z minus w and z minus the conjugate of w, I'm going to get z squared minus w plus w bar z plus w times w bar. And w bar, remember from last week, is the conjugate. So actually, this is very nice because this is real. This is just twice the real part of w. If you take x plus iy and you add x minus iy, you just get 2x. And this turned out, as we saw last week, to be the modulus of w squared. So what does it mean here? It means that if you did multiply it out, and by all means try it, well, what the hell? I mean, let's just do it. Let's just not believe it. Z minus root 3 over 2 plus I times a half times Z minus root 3 over 2 plus I times a half. We'll certainly get a Z squared. When I take the Z coefficient, I get negative root 3 over 2 plus I times a half there, and then I get another negative root 3 over 2. There's a minus here. There we go. So I'm going to get root 3 over 2 Z, another root 3 over 2 Z. I'm going to get minus I times a half Z, but I'm going to get plus I times a half Z, and that will cancel out. I'm just going to get minus root 3 Z. And as for this times this, they're complex conjugates, so I just get this squared plus this squared, which works out to be 1. So I'm going a little quickly here, but let's just suffice it to say that if you multiply those two factors out, you get Z squared minus root 3 times Z plus 1. And if you multiply the other two out, I'm just going to tell you the answer because I have no time, you get Z squared plus root 3Z plus 1. Okay, so what's the big deal with this? The big deal is we have factored this, Z to the fourth minus Z squared plus 1, into these two factors here with no complex numbers in the answer. They're just two real quadratics. They're both quadratics, and everything is real. So that's kind of nice. It turns out that any polynomial at all can be factored into either linear terms, Z minus something, or quadratic terms like this with real coefficients. That's a sort of very powerful theorem, as it were. So, anyway, this could be a legitimate problem, which would be described as factor Z to the fourth minus Z squared plus 1 into two real quadratics. That's what you have to do. You have to find the four complex solutions. You have to write them out as factors, and you have to identify within the brackets the conjugate pairs, root 3 over 2 plus I times a half, and root 3 over 2 minus I times a half, and just multiply those two out. You should get a real quadratic. If you repeat with the other two, you get a different real quadratic. That's how you solve this type of problem. It's pretty tricky, but it's still based on the same sort of idea, and that is that you have to solve equations of the form Z to the n equals something. In this case, Z squared. Well, there are a few other types of complex problems that come up once in a blue moon in Math 104. You can read about a few of them in the rest of Chapter 28, 28.5, 28.6, but I kind of have to move on to differential equations. I guess if there are any questions about this, I do encourage you to read the details in this 28.4.1, since I did it quickly. Have a question? Yeah, I did this last time. Basically, if you take any complex number, x plus iy, and multiply it by its conjugate, x minus iy, the difference of squares gives you x squared minus I squared y squared, which is actually x squared plus y squared. Right? X plus iy times x minus iy is x squared plus y squared. And this is actually equal to the modulus of x plus iy squared, because by definition, that modulus is the square root of the quantity. Now you want to see why w plus w bar is also a real number. Okay? So if I just take x plus iy up here and just add it to its conjugate, goes, the iy's cancel out. You just get 2 times the real part. Any number plus its conjugate is just twice the real part. Any number times its conjugate is its modulus squared. So actually, in both cases, you get real numbers. And that is why this expression here is a real quadratic. That's why that conjugate trick works. If you group the roots by conjugate, you get some nice stuff happening. Any other questions about this? All right, last topic in the course. Differential equations. Differential equations. Before I can say what a differential equation is, I need to do one thing. Clean the board. All right, this is a pretty massive topic in mathematics and a tremendously useful one in terms of modeling real-world behavior with equations. So, of course, in 1 and a bit weeks, we can only scratch the surface of the topic. First of all, suppose I write down something. We're working in chapter 30 here, the last chapter. Suppose I write down something like dy dx is equal to, say, minus 2y. Okay, that's a differential equation, meaning an equation involving derivatives. That's what a differential equation is. This says we have some quantity y, it depends on x, the rate of change with respect to x. So as x changes, well, that's minus 2 times whatever the value of y happens to be. In other words, when y is a big number, say 100, dy dx would be minus 200, which means y is getting smaller in a hurry. Whereas if y is only 0.01, then dy dx would only be 0.02, which means that y sort of gets slower, not so quickly. It's getting slower, but not very quickly. If y happens to be negative, in fact, y is minus 10, then dy dx would be 20, which means that y is actually growing. So the way y grows here depends on what y is. So it's a sort of feedback thing. And this is an equation of decay. It models radioactive decay of a sample. The more you have, the quicker it decays. That's the way of things. Of course, if I change it to plus 2y, you get population growth, rabbits, that sort of thing. The greater that number is, the faster they breed. The hornier they are. All right. So this is an example of a first-order differential equation. It's first order because we only have a first derivative. If we had a second derivative anywhere, it would be a second order, unless, of course, there was something higher. Here's an example of a higher order differential equation. X squared dy dx, the fourth derivative, d to the 4y dx squared, plus sine x times d2y dx squared times dy dx to the 7th plus e to the xy equals tan x. That's a pretty nasty differential equation. What is the order of it? Well, it's not 7. Just because you have a 7th power, no, it's the 7th derivative that would make it order 7. We don't have one of those. The highest derivative floating around is the 4th, so this is 4th order. In fact, the whole equation is 4th order. We're not going to be looking at 4th order in this course. We're only going to be looking at specific first and second order differential equations. Right, so the only other real concept that I need before I launch into the thing is that sometimes you might have something that looks like a differential equation, say dy dx is minus 2y, and y of 0 is, say, 5. So this is an example of what is called an initial value problem. But I will always call it an IVP. That means a differential equation and one or more starting conditions. This would mean when x equals 0, y equals 5. And in this specific simple case, I will solve this equation in generality, but because we've already looked at exponential growth and decay a little bit, we know, hopefully, that the solution is given by y is a e to the minus 2x, where we do not know what a is. A is some constant. Those are the only possible solutions to this. And as I said, soon we'll see why this is true. Let's just check that it's true. If y happens to be equal to a e to the 2x, then dy dx is minus 2 a e to the minus 2x. And you'll have to admit that this is actually minus 2y, because this, after all, was y. So the solution to the differential equation has this constant that we don't know about. But if we have an initial value problem, we can find out what the constant is by substituting into this when x equals 0, y equals 5. So this means that 5 equals a e to the minus 2 times 0. Right, I just took this solution here, and I plugged in y equals 5, x equals 0. And, of course, e to the 0 is 1, so this tells me that a equals 5. So the constant, which I didn't know, now I know, and in particular, y is 5e to the minus 2x. And that's the only solution. So it's basically finding the constant, the plus c, if you like. It's not a plus c in this case. It's actually an times a. And a is 5. So the initial value problem allows you to find the unknown constants. Question?
If that been a plus c, why are we multiplying in?
Well, the question is, why isn't it plus c? And of course, if you do have a plus c, it doesn't work, because dy dx, the c would go away, but it's still got to be there in the y. Soon, very soon, actually, I will show you the solution, show you why it's true that this is the case. And you'll see why the plus c is actually times a. Okay, so that's just the very quick overview of the sorts of things that we're looking at. We know what a differential equation is, we appreciate what the order is, and we understand an initial value problem is extra data that allows you to tie down some constants that may pop up. All right? So basically then, the rest of the topic is going to be looking at 3 different types of differential equations. Separable, first order linear, and first and second order with constant coefficients. Okay, I said that very quickly. They're going to be the headings, and hopefully I get through at least the first and possibly some of the second of those, and then next week we'll come back. So in 30.2, I look at what are called separable first order differential equations, diff EQs for short, or in Australia for some reason it's DEs. I don't know why it's diff EQs here, but whatever. Separable first order differential equations. Okay, so sometimes you get real lucky and you can rearrange your differential equation, taking a little liberty into y stuff times dy equals x stuff times dx. The liberty is that you split up the dy dx, which is sort of not really allowed, but then the chain rule kind of makes it all work anyway. So if you do that, it's separable. Or if you can do that, it's separable. So you want to separate, right? The y, everything to do with y is there, everything to do with x is there. So for example, if you have dy dx is equal to minus 2y, well, suppose that we divide, how do I want to do this? Let's divide both sides by minus 2y. dy, and that's just dx. I'm going to multiply by the dx and bring it up to the right-hand side. So you see it is separable. I've put all the stuff involving y on this side and all the stuff involving x on that side. Well, the next trick is just to integrate both sides. And of course, you integrate the left-hand side with respect to y and the right-hand side with respect to x. So here we get, well, minus a half log the absolute value of y is equal to, this is a 1 here, so it's actually x plus c. All right, we've gotten rid of the integrals and the derivatives for that matter. They sort of cancelled each other out. Now I just have to make y, solve for y rather. So I get log of y is equal to minus 2x. And I should really write minus 2c, but you know, minus 2 times c is just another c. I've relabeled implicitly without even commenting. Well, I'm going to comment now, but you don't really have to. Minus 2c to c. So what? Minus 2 times a constant that we didn't know what it is just some other constant that we still don't know what it is. Now, to solve for the absolute value of y, I better come over here for a little more room. I exponentiate both sides. So I get absolute value of y is e to the minus 2x plus c. And now we begin to answer your question up the front here. There's the plus c. It's in the exponent, though. We'll write that as e to the c times e to the minus 2x, and we'll call e to the c a. Actually, before I call it a, let's just leave it as it is. I just want to point out that absolute value of y, this means that actually y could be plus or minus e to the c times e to the minus 2x. And e to the c must be positive no matter what c is, but because of the plus or minus, that allows us to have negative values as well, which are acceptable. A e to the minus 2x, where I have dubbed a as this constant here. Actually, a could even be 0, which is not clear from this. This number cannot be 0. E to the exponentials are never 0. They're always positive. So plus or minus e to the c must be non-zero. So how come we screwed up? Well, if a is 0, this means that the quantity y is always 0. Both sides would just be 0 equals 0, and I wouldn't be allowed to divide by y. See, that's the problem. This assumes that y is not 0 for that to make sense. And if y equals 0, then you just get the solution here with a equals 0. So we're going to add that solution back, even though the method kind of screwed up. All right, very nice. So that is how you solve separable equations. This, of course, is a particularly easy and, well, common but very nice separable differential equation. Let me give you some more exotic ones just to show the technique. I'll give actually just one more. And then maybe I'll give an introduction to first order linear. Let's see how long this takes. All right, so here's a slightly more exotic equation. Consider this. dy dx plus cosine squared y cosine x equals 0. Doesn't quite look separable, but it is. Whack this on the other side first. dy dx equals minus cosine squared y cosine x. And divide by the cosine squared y to put it over there and throw the dx on the other side. In fact, when you divide by cosine, you get a secant. So actually, when I pull this over, I get secant squared y dy equals negative cosine x dx. You can put the minus on either side. It doesn't really matter. I'll leave it there. All right. Now all you have to do is integrate both sides. So the integral of secant squared is tan. And the integral of negative cosine is negative sine. And don't forget the plus c. You only need a c on one side, of course. This is sort of embarrassing. Maybe I made a mistake in my book. It looks to me like I'm going to have to just spontaneously change this example. Maybe I wrote it down wrong, Maybe there's a mistake in the book. The example I really want to do has a minus here. So unfortunately, I have prepared this example but written it down wrong in my notes and possibly in my book. So I'm afraid we'll rewind a little bit. The question was supposed to be dy dx minus cosine squared y cosine x equals 0. So when I throw this on the other side, it becomes a plus. And when I divide, I no longer have the minus here. And the integral of cosine is plus sine. And that's kind of how I wanted it to be, unfortunately. So please bear with me as I recover from this error and end up with the solution tan of y is sine of x plus c. So you might be tempted to write the solution y is inverse tan sine x plus c. The problem is, and it's similar to what we've seen in complex numbers, that if you know the tan of y, it doesn't mean y is inverse tan. For example, if tan of y happens to be equal to 1, then y could be pi over 4, which is inverse tan of 1. But it could be 5 pi over 4, 9 pi over 4, etc., or even negative 3 pi over 4, negative 7 pi over 4. What a pain. So you might have to add some multiple of pi to make this work. That's the only acceptable way to write this down, where n is an integer. So it's not actually 2 pi n like it was in complex numbers, because tan has period pi, not 2 pi. So this will work because tan of y doesn't care about the n pi. It just gives you sine x plus c. So I kind of think you should leave it like this. If you go there and you leave out the n pi, you kind of get it, you get it not quite right. To show you why it's important, let's consider an initial value problem. So an IVP of the same problem is this, dy dx minus cosine squared y cosine x equals 0. And I give you that y of 0 is indeed pi over 4. Well, if I have this, then I already know the solution to the differential equation is this. So I just need to say when x equals 0, y is pi over 4. So in particular, pi over 4 is inverse tan sine of 0 plus c plus n pi. And I have two constants to find out. Well, luckily, sine of 0 is just 0. So I have pi over 4 is inverse tan of c plus n pi. Well, I have to solve this. Really, I probably should have started with the equation. You know what? This is kind of a dumb way to do it. Let's go back. Let's start off with the equation tan y is sine x plus c. That's what I really should do here. Let's do this first. So when x equals 0, y is pi over 4. So tan pi over 4 is sine 0 plus c. And now we don't have to muck around with inverses. C is 1. Sine 0 is 0. Tan pi over 4 is 1. So this means that tan of y is actually sine x plus 1. Now we can go back to the other method and write that y is inverse tan sine x plus c, but we know c is 1, plus n pi. And we don't know what n is. But again, if we plug in pi over 4 is inverse tan 1 plus n pi, we see that, yes, inverse tan of 1 is pi over 4, and so n equals 0. And the solution in this case is y is inverse tan sine x plus 1. Now, in order to put this in perspective, suppose that I change the initial value. Instead, if y of 0 happened to be 5 pi over 4, very similar problem. This time I get tan of 5 pi over 4 is sine 0 plus c. Tan of 5 pi over 4 is again 1. So I get the same solution apparently. I still get tan of y is sine x plus 1. That's true. That's the same solution. But if I try to invert it, I now get y is inverse tan sine x plus 1 plus n pi. And here's where I really need to find out what n is. Because if I re-plug in 5 pi over 4 for y and 0 for x, I get 5 pi over 4 is inverse tan of 1 plus n pi. Inverse tan of 1 is just pi over 4. So you need 5 pi over 4 is pi over 4 plus pi. This means n equals 1. And in this solution, for this initial value problem, y is inverse tan sine x plus 1 plus pi. We'll have the extra pi there. So it's kind of a tricky little point. So what do I have to say about this? Well, this is pretty exotic. This is pretty exotic, this last little analysis. More or less, you'd be very unlucky to find that. But on the other hand, you do need to know the separable technique. You need to be able to recognize that an equation is separable. You need to rearrange it to put all the y stuff there and all the x stuff there. If you can't do that, it's not separable, and you're going to have to do one of the techniques from next time. If you can do it, integrate them both separately, don't forget the constant, and just solve the thing. So next time I will finish the whole lot with the last two types of differential equations. So until then.